So we're going to go through these three examples. You can pause this at any time. So the first, when we separate our variables, we're going to multiply both sides by dx to get the dx on the other side, and we get dy equals 0.2x dx. Now we take the antiderivative of each side. Antiderivative of dy is just y. On the right-hand side, we just have one of our regular antiderivatives. So 0.2x raised to the power by 1, so 0.2x squared, and divide by the new exponent, so divide by 2, plus c, or 0.1x squared plus c. Now we'll employ our initial condition to find c, and that was that y had to be 6 when x was equal to 1. So we get 6 equals 0.1 plus c, or that c equals 5.9. So our unique solution is y equals 0.1x squared plus 5.9. On the next one, we are going to have to do two things. We're going to move the dt to the other side, so we're going to multiply both sides by dt. And we're going to bring the p plus 4 to the other side using division. We never use subtraction or addition in separation of variables. So we get dp over p plus 4 equals dt. Now we take the antiderivative of both sides. We're going to get the ln of p plus 4 just equals t plus c. And we'll make both sides exponents of e to get that p plus 4 out of the natural log. So we have p plus 4 equals e to the t plus c, and we're going to absorb that constant. So we write it as a multiplicative constant, as we mentioned before. So p plus 4 equals, we'll call it a, e to the t. So to solve completely for p, we get p equals a e to the t minus 4. And we'll now employ our condition of 0, 100. Okay, so that tells us when t is 0, e to the 0 is 1, not 0, be careful. The a is not automatically 100. What we get is that 100 equals a minus 4. So a is going to be 104 for our problem. So our unique solution is p equals 104 e to the t minus 4. In our final example, we have to do one step before we separate our variables. We cannot separate with addition or subtraction. In this case, we're going to factor out the z. So dz dt is going to equal z times 1 plus t squared. Now we're going to leave. Now we have to think about how to separate these. We want the dt to come over here and the z to go down here. So dz over z is equal to 1 plus t squared dt. Antiderivative of both sides, we get the ln of z equals, we can do this piece by piece, t plus t cubed over 3 plus c. Again, we'll make both sides exponents of e, so z is equal to e to the t plus t cubed over 3 plus c. And absorbing constants will make it a multiplicative constant yet once again. So z equals a times e to the t plus t cubed over 3. And subbing in our initial conditions, we'll be able to solve. So when t is 0, e to the 0 ends up being 1. So 5 ends up being equal to a in this case. So our unique solution is z equals 5e raised to the t plus t cubed over 3.